examples to do, so I'm just going to start going here. This is a continuation of 4.6. Let me zoom in here a little bit. Whoops, a little bit too far. There we go. That's okay. Modeling with exponential functions. There were two types of modeling that we didn't get to yesterday, so I wanted to start out today with what those were. The first thing we're going to look at is known as radioactive decay. When you have certain elements, they emit what's known as radiation. The rate at which they emit that radiation is known as the rate of decay. The rate of decay is proportional to the amount of material. It is generally given as a percent. However, the most common is 50%, and this is known as a half-life. Half-lives are used in dating objects because if you can figure out how long it takes for that particular material to go down by half, then you can work it backwards to get a date. So, for example, we use the half-life of carbon when we're dating bones for archaeology, and the half-life of radium, which is a radioactive substance, is like 1,600 years. So if a 100-gram sample decays to 50 grams, we know that 1,600 years has passed. All right, so a radioactive substance with a mass or amount of M0, where that's our initial, and the half-life H. The amount remaining at time t is modeled by m of t is equal to m sub 0, 2 to the negative t over h. And again, m sub 0 is our initial amount. T is the given time. And H is your half-life. how long it takes for the half-life. All right, to find the relative decay rate, that basically means any other decay rate that's not by half. To find the relative decay rate R, we use an m of t is equal to m sub 0 e to the negative rt. So just like our growth rate, remember our growth rate was n sub 0 e to the rt. Now, because this is decay, it's not a positive RT, it's a negative RT. Okay? So these are essentially the two formulas that we use. So for the half-life, if we're given a half-life, we'd use this one. And if we're given a relative decay rate, we use this one. Now, it's worth noting that sometimes we are given the relative decay rate and asked to find the half-life. So this would be something like, we're told it decays by 10% every 2 years. What would the half-life be? It's not as easy as just taking 10 times 5, because remember, you're taking 10% off each time. So it doesn't stack. Like you can't do 10, 20, 30, 40, 50. It just doesn't work that way. So what we do is we start with this relative formula. M of t is equal to m of 0 e to the negative rt. Now remember, half of that would be m of 0 divided by 2. And our time we're gonna use the relative to find the half-life. Okay? So if we start with the original relative equation, we have m of t is equal to m sub 0, or the initial amount, times e to the negative rt. If we want a half-life, then the amount left is going to be 1/2 of m0, 1/2 of the initial amount, or the initial amount divided by 2. Okay, that's where that's coming from. So this is going to be m0 e to the negative rh, because we want our time to be the time for the half-life. if I take the m sub 0 and divide it out of both sides of this equation, I'm just going to end up with 1/2. So the half-life is at e to the negative RH. Now, I'm just going to take the natural log of both sides because this is an e. So if I take the natural log, the natural log e is going to cancel. And I'm just going to have the ln of 1/2 is equal to a negative RH. Well, the negative RH could come out front. Then ln E is just 1. So I'd have an ln1 minus an ln2 is equal to a negative R times H. Now, what's ln1? Nope, no 10 here. This is a natural log. That's the E. ln1 is 0. Any log of 1 is always 0. It doesn't matter if it's a natural log or an ln. It's always going to be a 0. So what I have here really, put this up here, is a negative ln2 is a negative RH, dividing both sides by a negative h. I have a generic formula that lets me know if I want to find the relative growth rate, I can just use ln2 divided by the half-life. Yes, I divided by negative h. Oh, okay, hold on. Something's missing here. Okay. All right, so let's try an example. Okay. Polonium 210, radioactive material, has a half-life of 140 days. Suppose you have a sample worth or in the amount of 300 milligrams. Write a function to model the relative decay rate. Find the mass after 1 year. And determine when the mass will be 200 milligrams. Okay. All right, relative rate of decay. M of t is equal to so initial is how much? Yeah, no. What was the initial amount? That's our m sub o, or m sub 0. It'd be negative RT, you're right. And remember, the rate is the natural log of 2 divided by h, your half-life. Now, they didn't give us the rate here, so we have to use this half-life conversion because that's what they gave us, right? So we're going to do 300e to the negative ln2 over 140 times t. And the hard part, at least not hard, but the weird part, is that all of this is my exponent. Okay, so this is my equation, or my function. All of this. That whole bit's the function bit. Okay. Now find the mass after 1 year. We've got to be careful here. In the original problem, our time was given in days. So I can't suddenly switch here to years. I have to use 1 year as 365 days because my time has to be in the same unit. Therefore, my m of t is m of 365. And that's going to be 300 e to the negative ln2 140 times 365. Okay? So now when I type this into my calculator, 300 e to the, I type it all in at once, unless it's really obvious, right? Like if that had been a 70 rather than a 365, 70 and 140 cancel. So I would have done some stuff real quick. But if it's not obvious, I just put it all in. Negative ln2, and it would be times 365 divided by 140. And I'm getting like 49.2 grams. That doesn't seem right. Did I forget to close my parentheses? No? Okay. Okay. 49.2. Checked it twice. We're good. Yep. Okay. Just checked my answer. Okay. Yep. Mm-hmm. No. Oh, you didn't close your parentheses after your ln too, did you? Okay. Okay. All right. So there we go. And then the last one says, when will the mass reach 200 milligrams? So this is saying if m of t is equal to 200, we've got to find t. So 200 would be 300 times e to the negative ln 2 over 140 times t. Again, all of this is my exponent. So, yep, I'm going to, the big idea here is I need to bring this down out of the exponent. So I'm going to divide by 300 first. That's going to be 200 divided by 300. That's 2/3. Then because this is an e, I'm not going to take a log base 10. I'm going to take a natural log. ln of 2/3 is going to be ln of e, which is going to bring all of this out front. Now I'm trying to isolate t. I'm going to multiply by 140 over a negative ln 2. Is it okay if I do that in one move for you? Right, multiplying by the reciprocal. So I'm going to have 140, and then ln 2 over 3 is going to be an ln 2 minus ln 3 over an ln 2. Put a negative on here somewhere. I'm going to put it up top. Doesn't matter where. Well, no, because it was being multiplied, so I would need to divide it on the other side. Right? We multiplied by the reciprocal. Reciprocal would have put the ln 2 in the denominator. Oh, on the calculator, I would just do the whole numerator. Oh, you could put it anywhere, right? I just need to put one negative on here. It can go on the top or on the bottom. Yep, negative 140 parentheses, ln 2, remember to close my parentheses, minus ln 3, remember to close my parentheses, and that hit equals, to get like a 56.8-ish, but then I still need to divide that by ln 2. And I get an 81.89, or about 82 days. Which kind of makes sense, because at 140 days, they should be at 150, half of 300, because 140 is our half-life. So after 140 days, we would have 150 left. So it should take less than 140 days to get to 200, and we got 82. So, okay. I'm all right with that. Okay. Great. Okay. The last law has been a big hit in previous terms. I don't know if it will be this term or not, but okay. This is known as Newton's law of cooling. All right. And previous terms, I mean, it's a little bit morbid, but previous terms, students have liked it because it's actually like a forensic files kind of thing, if you're into that piece. So Newton's law of cooling says the temperature at time t is equal to the temperature of the surroundings plus d sub 0, which is the initial difference between the room you're in and the temperature of an object, times e to the negative kt, where k is a positive constant that depends upon an object, and t is your time. So just to get these written out, T sub t is temp at time little t. T sub s is the temperature of surroundings. So if you're in a room of 72 degrees, then T sub s is 72 degrees. If you're outside and it's 98 degrees, then T sub s is 98 degrees. D sub 0 is the initial difference between the surroundings and the temperature of object. So if we're talking about putting an ice cube in a 72-degree room, right? Then D sub 0 would be 32 degrees for the frozen ice cube minus 72 degrees for the room. So it would be that 40-degree difference. Okay? All right. And we'll do a couple of examples so that you can get some of these. K is a positive constant. And it's sometimes given and there's a couple of problems where you have to find it. But in the beginning, it's basically given to you. Okay. So a little bit morbid, but here we go. Here's a forensic files example about the time of death. All right. Let's say that a normal body temp is 98.6 degrees Fahrenheit. This does vary some from person to person. I know mine is 97.7, 97.8. I know I'm a little low. But in general, it's agreed upon that the normal body temperature is 98.6 degrees Fahrenheit. K in humans, right? So that's our positive constant for the formula. Is K is equal to 0.1947. Suppose room temp for this given room is 60 degrees Fahrenheit. So without giving you like a long drawn out story, here are the three pieces of information that we've been able to pull. All right, so we want to model this information using Newton's law of cooling. Our initial formula is temperature at time T is equal to the temperature of the surroundings plus the initial difference between the surroundings and, in this case, the body, times E to the negative K times time. All right, what is the temperature of the surroundings?
60.
And the difference between the surroundings and the body temperature? Yep, that's going to be the 98.6 minus the 60 degrees times E to the negative K, 0.1947 times T. So I have 60 plus 38.6 times E to the negative 0.1947 T. And that's my formula. There is actually a problem a little bit later. You'd need more information than you were given here, but you could go back and find K. Yeah. Yeah. It's a challenging problem, that one, in terms of everything we've done so far. But I think I do give you one like that. I'm pretty sure there's one like that in the homework, just to challenge you and see if you can do it. But that's not something that I would necessarily put on a test unless it was a take-home part, right? Like in a regular term, there's usually one close to that or in a similar challenge because it's on the take-home part. But we don't have a take-home part. Not this term anyway. Okay. If the body temp measures 78 degrees, how long has it been dead? So what is 78 degrees in this case? Keep in mind, you've got this one, you've got this one, you've got this. Yep. So this 78 degrees Fahrenheit is our T of T. And now I just have to solve this natural log like I've been solving them all along, right? Subtract 60 from both sides. I'm subtracting, right? But then I'm going to divide both sides by, yeah. And when I do that, it didn't come out even, right? So what I'm going to do is I'm just going to leave this as 18 over 38.6. Because I don't want to gunk up my calculator with some decimal that doesn't end. So I'm just going to leave it as 18 over 38.6. Now what am I going to do to both sides? So when I take the natural log, I'm going to do two steps at once here. When I take the natural log, that's going to be an ln 18 minus an ln of 38.6. And when I take the ln of this side, it's going to cancel with the e, and I'm going to have a 0.1947t. I'm going to divide both sides by that k value, negative k value, and that's going to give me t. So what's my time? It's that parentheses every damn time. You got something? Yeah, and I also got like a 3.918. No, I'm still typing because again, I forgot the parentheses. All right. So I got 39.18 and the time would be in what? No, I don't think this is days. Is our time always in hours? Hold on, let me double check. I just want to make sure our time is in hours here. The time t modeled by. No. I would too. Yeah, this doesn't say. So whatever function of time I guess we use, I don't think it's minutes. Where is it? Yeah, t is hours. You want to try one where we have to find k? All right. This is from the text. It's number 27. We're cooling a turkey. Okay, a turkey is taken out of the oven. At 185 degrees Fahrenheit and left in a 75 degree Fahrenheit room. This is all the information we're getting to start. If the temperature of the turkey is 150 degrees Fahrenheit after 30 minutes, find K. And then part B says, what is the temperature of the turkey after 45 minutes? All right, so if we're working on part A, we're going to first start with our formula. T of the temperature at time T is equal to T sub S, or the temperature of the surroundings, which are 75 degrees, added to the difference in the initial temperature and the room. It's 110, right? E, yeah, I didn't do this. I did the subtraction in my head. So 185 minus 75 is 110. To the negative K, and then T is time. All right. So part A tells us that the temperature of the turkey is 150 after 30 minutes. So this becomes my temperature at time T, and 30 minutes becomes my T. That's not so bad, is it? So I'm gonna have 75, because 150 minus 75 is 75, is 110 e to the negative 30k. So 75 over 110 is going to be e to the negative 30k. Now, can I do two steps at once again? Yep, or divide by negative 30, either way. I got a 0.12766,408. Correct. Okay. All right, and this gets us the K. And then part B says, what is the temperature of the turkey after 45 minutes? So that's just taking the temperature at 45, 75 plus 110, e to the negative 0.01276 times 45. Now, this is just my advice to you. It's not a hard and fast rule, but my advice would be, if you have to find the K, to keep at least 5 decimal places, right? I've kept 6 here, but keep at least 5, because otherwise it could round you too far off. And even at 5 sometimes. So if you run into something, don't be afraid to reach out and say, hey, I've kept, 4 or 5 places here and I keep getting the wrong number. Once I've got K, now I can just plug it in for 45 minutes. Point 0.012766 times 45. That seems wrong. Hold on, let me try this. There we go. It's like, that's not the answer I got the first time. It definitely shouldn't have gone up in temperature. So when I got an answer of 270 degrees, I knew it was wrong because it came out at 185. So it shouldn't have gone up. All right. That should do it. Okay, so just as a reminder, this homework on the modeling stuff is due on Monday. And so Monday, I will pop into class and I'll hang around for a while to see if anybody else shows up, in case there are questions on modeling these problems or on anything else from the chapter. And then Tuesday is also scheduled to be a Q&A. So if Monday all we do is modeling questions, then Tuesday I will also be popping in for a while in the beginning to see if anybody shows up and has further questions. Questions for Monday and Tuesday. And I will show up at least for the first 10 or 15 minutes both of those days in case anybody's running late. Okay? Any other questions for me, Landon? All right. You have a good weekend and reach out if you need anything, all right? Thank you.